before we dive into proper circuit diagrams, we're going to do one more kind of more physical batteries and resistors. We're going to look at some linked resistors or wires. Basically two linked elements that have some resistance. We're going to do a little more quantitative than what we've thought about, but not quite as a circuit yet. All right, so let's draw out something like this. We've got one piece connected to another piece like that. Okay, so this one, part one, it has one resistivity. This is part two, has a different resistivity, and they're just fused together like that. They each have the same length L, like that, and they each have the same A. The area is constant all the way across. So you know how you could get the resistance of each one if you wanted to. And then we're going to hook a battery up to them and see what happens, a battery with EMF like that. And let's see, we'll call that positive, negative, and we'll connect a wire like this. So the wires are highly conductive, much lower resistivity than the element, so the wire just transmits the potential, you could say. All the action will happen in there. All right. So what we want to do is just figure out what are the different currents in these two things, what are the different potential drops, voltage drops, what's the power. We'll just go through all those numbers real quick. So for the current, there's one fundamental idea here, and that's the current is the same in each element. It's the same in each element since there are no junctions. As we know, the current is the flow of charge. We know charge is conserved, so current is conserved. So whatever current flows in that wire has to be the same current flowing there, flowing there, flowing there, flowing there. It can only change if you have a junction. So the current is the same, but there's no reason the voltage drops have to be the same. But delta V could be different. So I think in a previous video, we said that delta V had to be the same because there was one common point that was across each element, but that's not the case here. We have the delta V for this first one would be between here and here, and that is not the same 2 points as for this one between here and here. So when these two things are in series, as we're going to call them later, they have the same current, but they'll have different voltages. So that's one physical insight to be working on. And here is another one. Just this is more of a procedural insight. And this, so there, the current's the same. Those are different. Here is Ohm's law. And I'm going to leave off the quotes just because I'm just tired. Ohm's law applies between any 2 points in the circuit. Applies between any 2 points. Now I won't say in the circuit because this isn't a circuit yet. We're just talking about batteries and wires and resistors. Okay. So you can apply Ohm's law to the entire circuit. You can apply Ohm's law just to this thing. You can apply Ohm's law just to that thing. You can apply it to the wire and this thing. And the voltage drops and the resistances and the currents will always work out. Okay, so Ohm's law applies really anywhere in a circuit, any 2 points. So let's go ahead and apply it then. Let's talk about delta V across this element, the voltage drop 1, and across that element, voltage drop 2. And if you set it up right, you know enough to solve the problem, although we're not doing this one numerically, so we're just going to solve these symbolically. Okay, so delta V1, let's see, if this were some problem where you had numbers, what would you want to write down? Well, you know delta V1 must be the current times R1. Sure, so whatever the resistance of that is. You know delta V2 must be the current times R2. Now, why didn't I put a subscript on the I? Because I is the current. And what did we just say? The currents are the same. I could write I1 and I2 and then point out that I1 and I2 are the same. But usually it kind of looks nicer and makes more sense to not put a subscript on the things that are the same, because then you immediately look at that and say, oh, they're the same. All right, so there you go. If you wanted to get it in terms of what you were given, we just plug in for the R's. Okay? So we'd say delta V1 equals I, and then R1, so the resistance of a cylinder, rho L over A. So it'd be rho 1, the length over the area, and delta V2 is rho 2, length over the same area. So I left out the I. There's something was wrong. Delta V2. So the voltage drop across the second one is that, and the voltage drop across the first one is that. So, so if we wanted to figure out which one is larger, the question could have been which one gets more of the voltage drop than the other. It would just depend on the relative resistivities. The one with a higher resistivity is going to have the higher resistance and therefore the higher voltage drop. So if rho 2 is bigger than rho 1, rho 2 is bigger because R is bigger, those go together, delta V is bigger. Let's see. So a general rule when you have two things in series like this is more resistance, more delta V. Okay. Not a universal law, but that's the basic idea. Now let's see, what about power? All right, so power. Let's think about our equation for power. Power dissipated across a resistive element like this is the current times delta V. All right, so the power dissipated in 1 is I delta V1, and the power dissipated in 2 is that same current, delta V2, the voltage drop across 2. So we get the same thing. Bigger resistance, more power is going to be dissipated. In this simple case of just two simple things in series with the same current going through both. Okay, that's interesting. But what we can go a little bit further here, I'll just write it again, more resistance, more power dissipated. But what we can go a little further is we can see sort of how the voltage, how things add, okay? So now if we think back to what does potential difference really mean? What is a voltage drop? So remember, it's a drop in the electrostatic potential from here to here and here to here. And we say in the wires, there's essentially no drop. The wires are such low resistance, you can get current flow with essentially no delta V, no voltage drop. So the potential here is still essentially plus E, and we'll call this 0. So it's plus EMF all the way to here, plus EMF volts, and 0 volts all the way to there. So you can see, based on how electrostatics works, even though we're flowing, the steady state current flow, that whatever voltage drop we get here plus here has to be equal to the EMF. Okay, so in series, so voltage drop in series will obey this. The EMF will be equal to delta V1 plus delta V2. Okay. Right, so just like if we were doing a uniform field and said we have the higher potential, equipotential all the way down to the lower, if we took that difference and just cut it in half, that's basically what this is. Here's part of the potential drop and here's the rest. If you don't get this intuitively and you don't quite see it, later we're just going to tell it to you like dogma. It's going to be one of Kirchhoff's laws. So for now we're trying to get a physical feel for it. We could then look at it and say, okay, if that's true, what are those delta V's? What are those voltage drops? We could say, okay, well then the EMF, we could go all the way back up to, let's say here, and this is I times R1, and we could say, what is this one? I times R2, and then we could pull out the I, and we could say equals I times R1 plus R2. And this is something that when we get to circuits we'll call the equivalent resistance. The battery is not sentient. It doesn't have, these aren't eyes. They kind of look like eyes. It can't look at that and say, oh, it's two resistors in series. I better apply the right delta V's. It doesn't know that. All a battery does is apply an EMF, and based on what it senses overall, it sends out some current. Okay, so this is kind of like what it senses overall. So it's also called the equivalent resistance. So REQ is what we'll call it later when we're doing circuits, is R1 plus R2. For two resistors in series, the resistances just add. Okay, and you can see that if you basically accept this idea, that the EMF drop across the whole circuit is equal to the delta, the EMF applied to the entire circuit, it breaks up into the two delta V's across the things in series. Okay, but here we weren't trying to get to this. We're going to give you this again later. We're just trying to get the idea in your head. Current flows and voltage drops and resistances.